Hello, I hope you're doing really well today, and we can celebrate because we finished chapter 10 and we're moving on to chapter 13. You should have already done the vocabulary for this chapter, and yesterday you watched a pretty good introductory video, but I want to take some more time with the material in section 13.1 to go over some of the things that he didn't really go over in the video, plus to clarify a few things. And so I have a glass of water with me, because that's what we're talking about in this chapter, water. In fact, I'm going to put this on the floor because this is just a disaster waiting to happen. There we go, all safe. Okay, so this section is called Uniquely Water, which is kind of a weird title if you think about it, but it does make a lot of sense because water has some amazing properties that we're going to talk about today. So first of all, it's kind of neat that in its natural state, normal earth temperatures, water exists in all of the three common states of matter. Water exists as solids in the form of snow, glaciers, ice caps, things like that. Of course, water exists in nature as a liquid in our oceans, lakes, streams, all those kinds of things. And then it exists as a gas in water vapor, like humidity in the air and in clouds. And so I think that's really cool that God designed water so awesomely that it can go in all three states of matter in the normal range of temperatures for Earth. And also want to talk about the fact that it is a polar molecule. Now remember, the formula for water is H2O, and so you'll have one atom of oxygen and it's covalently bonded with two atoms of hydrogen. That's how we get the formula H2O, because there are two hydrogens, one oxygen. And I'm going to pull from some other things that you've learned in other chapters, like the chapter we did on electronegativity. He didn't mention electronegativity in the video, but remember, electronegativity is the measure of the attraction that an atom has for electrons when it's in a chemical bond. And each element has its own value for electronegativity. If you look at the values, oxygen is much higher than hydrogen. I don't have the numbers right in front of me, but trust me when I say oxygen is definitely a higher value. And so in each of these bonds, this is a separate bond, this oxygen with this hydrogen, and then this oxygen with that hydrogen. In each of those bonds, oxygen, he called it, is hogging the electrons. It's basically pulling the electrons more toward itself. I don't know if you caught this, but I did not care for the fact that in his little atomic diagram, he had the electrons circling the atom. That was very bad, very wrong, not good. You know that doesn't happen. A little upset about that, but the rest of the content was pretty good. So anyway, basically oxygen has 6 electrons normally, and they're just kind of buzzing all around. The valence electrons are buzzing all around. Actually, it has 6 valence electrons. It's got more than that total, but 6 valence electrons, and they're just like buzzing all around. But hydrogen each has 1 valence electron, and it will buzz kind of near the hydrogen, but more near the oxygen. And so hydrogen still thinks that it has 2 valence electrons. And so these are held together by covalent bonds. And we do say that there are partial charges. And you'll probably remember this from earlier in the year. Okay, but oxygen actually has 2 lone electron pairs. When we did another chapter where we were doing like the 3D structures of molecules, remember when we were doing our toothpicks and the candy, we had a piece of candy to represent each hydrogen, we had candy to represent the oxygen, and then we had empty toothpicks to represent these lone pairs because they do affect bonding. And so these themselves have a partial negative charge. And I just drew the Greek letter delta. And whenever you have a delta negative, that stands for a partial negative charge, meaning that it's not as much of a negative charge as an electron would be by itself, but it's in that negative spectrum of things. And so again, less powerful than a full-on electron, but there definitely is a lean toward having a negative charge there and there. And then if oxygen has partial negative charges, of course, hydrogen would have to have partial positive charges. And so we're going to note that by putting the little delta and then a plus sign for each one of these. And that's what makes water a polar molecule. It's unevenly dispersed. Like, you definitely, clearly, very distinctly have positive regions and negative regions. And so water is a very polar molecule. And if it was just by itself, that'd be awesome. But when you put it together with a lot of other water molecules, it makes the individual water molecules attract to each other. Now, if this is liquid water, like you'll have another water molecule come up, and the oxygen end, remember this oxygen end would also be partially negative. It's going to want to be near this partially positive one, because remember, opposites attract. And so even though because it's a liquid, it's going to have to keep moving around and stuff like that. So it won't be able to stay here very long, but it's going to kind of hold and pause there a little bit as much as possible. And then it's going to move on, and this oxygen is going to kind of tumble and turn throughout the liquid, and it's going to try to find another hydrogen to be nearby. And it's going to be standoffish against other oxygens, because those are negative, just like this. Like charges are going to repel. So in a liquid, you have these strong cohesive forces, which we'll talk about again in a minute, between all of these oxygen and hydrogen combinations. And in fact, whenever you have these, like say it's cold enough where it can slow down and freeze, if it freezes in place, this would be what we call a hydrogen bond. Now, there's no physical connection here, but there's a definite attraction, and we call that a hydrogen bond. It might be a little deceptive because we're only talking about water in this chapter, but hydrogen will actually hydrogen bond to other highly electronegative atoms like sulfur and fluorine and things like that. So just kind of keep that in the back of your head for future times. But since we're just talking about water in this chapter, this is a great example of a hydrogen bond. And so if there's low enough kinetic energy that the water particles can freeze in place, then it will create a nice, even, open structure. And that leads into the fact that water, when it's frozen as ice, is less dense than liquid water. And that's really important in nature, because if you think about a pond up north that would freeze over in the winter, it freezes from the top down. If water froze from the bottom up, every single fish would die, plants would not be able to live. It would create a lot of problems. But because an actually protective layer of ice forms on the top of a lake or a pond, it lets water stay underneath, and the fish can kind of slow down a little bit. Plants can still live and things like that, so you don't have total devastation every winter. So that's a really cool thing. And you know that ice floats. Like if you have a glass of water, you put ice in it, it's going to float to the top. And so, but nature has many more important things to say about that. And then I want to talk about the cohesive forces of water particles again. Remember, you have all those hydrogen bonds. And so whether it's frozen as a solid or a liquid, you're going to see an effect from this. And so if you think about like a beaker full of water, if you think about a particle that's not at the surface, okay, just like a random one, like maybe right here. Okay, that doesn't even show up. Let me try that again. I cannot make this show up. Let me switch markers. Marker problems, right? Okay, so let's say that we have like a single, now that's obviously way too big for a single molecule, but basically it can be pulled in 4 different ways, because if you look at it, this hydrogen can be attracted to something, that hydrogen can be attracted to something, each of these lone pairs can be attracted to something, and so there's a 4-way pull in 3 dimensions on this one right here. But if you have a particle that's at the very surface, okay, nothing can pull from above. It can only get pulled from the sides and below. And so it's going to create like a little invisible film. It's not an actual like different substance or anything. It's just basically a layer of the water that's all being pulled together downward and inward, so that it's hard for certain things to break it. And so if you have like a little leaf that falls on the surface of a pond, or maybe a little tiny insect, they can crawl across. You even saw that I think it was in the video, that he suspended a paper clip on top of the water, which was pretty cool. So you can actually suspend things on top of water. All right, so that's surface tension. And I also wanted to point out the fact that like if water is just like only water, it's not even in a container, it will naturally want to form a ball. Now, it won't do that like a lot, like if there's a lot of water present because of gravity, like it'll make it fall down. But if you get a little tiny water droplet, like on a leaf, maybe from dew or something like that, it'll bead up And if you have something that's like not very adhesive toward the water, it'll beat up on top of it. And if they're like raindrops, they would be round, but for gravity, so raindrops actually end up being more like a teardrop shape. But if there were no gravity, you would see it just like be a nice little sphere. So I just wanted to point that out too. Okay, so cohesion is a property where water molecules will attract each other, or molecules or atoms of any of the same thing will attract each other. Adhesion is where water will attract to something else, or one substance will attract to something else. And so if you have like water in a graduated cylinder, you'll notice that at the very top it forms this little U shape. And I know he mentioned it in the video. It's called a meniscus. And you measure from the bottom of the meniscus. And so I didn't draw any of the markings on here, but that you would just kind of eyeball it over and measure whatever it says on the bottom, because the parts that are cleaning up are only doing that because of the adhesive properties of water. And you'll see water do this more so with certain materials. Like water loves to adhere to glass. Some plastics will also cause water to creep up on it. And so I mentioned meniscus. We also want to talk about capillarity. If you have a really thin tube, water will get sucked up in it because water keeps being attracted to the sides of the tube. This works really well in a glass tube. And maybe you've had your finger pricked at the doctor before. Your blood is mostly water. And the nurse or whoever's drawing the blood will just stick the end of a little tiny glass stick that's hollow in the middle, and it'll just suck the little droplets of blood right up because of the adhesive properties of water. And so that actually has some medical applications as well. And then we just talked about specific heat in the previous chapter that we did, but I want to mention it because the specific heat of water is super high. And that's actually a really good thing, because we can have lakes and streams and pools, bodies of water that will not evaporate even though the heat is extremely high. And so this is really important. It will make sure that our oceans and rivers and ponds and all that do not evaporate, especially in the intense Florida heat, because it can get pretty hot in the summers. It's even starting to get hot now. I don't know if you noticed yet. So the specific heat of water is really, really important, and it makes water a good coolant. Remember, it's because water has a high heat of vaporization. The heat of vaporization is the amount of energy that it takes to raise the temperature of 1 kilogram by 1 degree Celsius. And so water is really awesome compared to most other things, and that's really good. I also want to talk about the fact that water is, quote, a universal solvent. Which you would think it would mean it would dissolve everything. And it doesn't really dissolve everything, because everybody knows water and oil don't mix. You can't do like water and wax and stuff like that. But water will dissolve many, many things. Like the vast majority of things will actually dissolve in water. And so we have this phrase, like dissolves like. And so if something is nonpolar, and it doesn't have like some of the oils and stuff that we have, and it doesn't have like those positive and negative regions on it, it will dissolve something else that's nonpolar. So like if you're working with, let's say a stain, like you're going to refinish some furniture and you want to stain it like a dark color, that stain is nonpolar, and you have to wash up and clean up with something nonpolar, such as mineral spirits. So oils and stuff like that would work, but then you have oil so on your hands and stuff like that. So you have to use something that is like or similar to the substance you're trying to dissolve. And so whenever we have water, which is polar, whenever we have water, which is polar, it does really well dissolving other polar things as well as ionic things. And so a good example of something ionic that would dissolve well in water would be good old table salt. Okay, so table salt is sodium chloride, NaCl, and as soon as you sprinkle salt into water, the salt is going to split apart. So you'll have positive sodium ions and negative chlorine ions. Remember, the hydrogen ends of water are partially positive, and so the chlorine ions are going to want to hang out by the hydrogens, because chlorines are partially negative, or chlorines are actually negative, and then the hydrogens are partially positive. So the chlorines are going to spread apart, and they're not going to want to be by the oxygens, because remember, the oxygen ends are partially negative And so they're going to say, I don't think so. I would rather be by the hydrogen. And so they're going to kind of try to do this. Now, if they're in a liquid, they're going to have to keep moving. They have a lot more kinetic energy than it would allow them to be still. And so they're going to keep moving, but they're going to find their next available hydrogen and just keep moving along like that. And then the sodium ions, remember sodium is a positive ion, and so it's going to want to hang out with oxygen. So it's going to find the first available oxygen and kind of try to be by that for a while, and then it'll have to move on and it'll try to find its next available oxygen. And so things that are ionic, like all of those compounds that have your metals bonded with a non-metal, like barium chloride, potassium iodide, anything that has something from the left of the periodic table to bonded with something from the right of the periodic table, those are going to do really well dissolving in water because water is very polar. Things that don't do well dissolving in water would be things that are non-polar, like oils and waxes and things like that. And I think that's about all I want to say. So I think I covered this section. It's 13.1, and the guy in the video covered some of it already, but I just wanted to make sure that I went through and really thoroughly covered the material. And you have a few questions, of course. So once you're finished with my video, please go ahead and answer those questions on the Google form, and then continue to put in prayer requests and comments and things like that, because I do read them. I do pray for your prayer requests, and I'm interested in knowing how you're doing. And this is a crazy time. So just take it one day at a time, and we'll all get through this together.